Recording is rolling. Yeah, so welcome to Monday. This is week 2 of studying forces. You guys remember last week we were studying forces, Newton's laws of motion, free body diagrams, and that sort of thing. And I did assign to you guys these problems, a few from chapter 4, a few from chapter 5. So today we'll go over about half of those. And then tomorrow the plan is to do more textbook problems. So today and tomorrow we're doing a bunch of textbook problems. But then, finishing out this week is going to be a lot of labs. Got Atwood labs lined up for you guys. You guys remember that involves like a pulley and a string and some weights, right? Some of these. So that should be really fun. I've got a really cool one lined up for you guys on Friday. It's a lab tech activity. And then I still have to do a friction lab with you guys, so that'll probably be next week. So yeah, after today and tomorrow, a lot of the lab tech stuff coming up. But before I get to the physics stuff, I got in my mailbox this morning this yellow ballot to vote for Teacher of the Year. And I have 1 day to get this in, so today's the day that we're going to do this activity that I always do whenever I get this ballot. Okay, here you go. Right, so I want to tell you guys about a little bit about voting systems. So there's many different kinds of voting systems out there, and this is one field of science, right? So like the science of elections. Now, I want to tell you guys about these two different systems. So these aren't the only voting systems, but these are just the two I'm going to talk about because I want to contrast some of these ideas. Okay, so first past the post system. This is the idea that say there's a list of candidates, just like right here. There's these 5 candidates, and you go to the ballot box, you vote for one, just your favorite one, and you walk out, and that's it. And then at the end of the day, all the votes are tallied, and whichever candidate has the most votes wins the election. And like that's straightforward. Like that sounds pretty straightforward and fair, right? Like, everybody gets one vote. Whoever has the most votes wins. Well, there's a problem with this type voting system, and here I'll give you guys an example. Suppose I'm going to have you guys vote in a few minutes, but just give some example numbers. Let's say when I have you guys vote that maybe Mr. Egan gets like 40% of the vote, and then maybe Ms. Hudgens gets 20%, and then 20%, and 10, and 10. So it goes 40, 20, 20, 10, 10, like in terms of the percentages. In that case, who got the majority? Who got the majority of the votes? And the answer is no one. Yeah, nobody got the majority. No, you might say Mr. Egan has the plurality, he's got the most number, but majority means more than half, like more than 50%. And that could raise an issue of, like, well, what if all the people who voted for these other 4 teachers had they not split their vote, maybe they all would have voted for like Ms. Hudgens, just for example, something like that. Well, maybe Ms. Hudgens could have been preferred by the majority, but this first past the post type system would not have revealed that information. Okay? And so this leads to a couple concepts. There's something called strategic voting, where, well, now you can't really vote for your favorite. You have to say, well, who's my favorite, but also how is everybody else voting? And then I have to sort of figure that out. And then if there's like poll changes, it also leads to a problem called the spoiler effect. Because there might be, say, one of these teachers that you really, really like a lot, but you know that if you vote for them, maybe if they don't get many votes from anyone else, that you would effectively be throwing your vote away, right? So it causes problems like this. In the United States, we use first past the post type system for pretty much all our elections, and it causes all these problems I talked about. It also creates an election environment that really realistically only allows for 2 parties, because once you have a third party, again, runs into the spoiler effect, and then if you cast a vote for, say, a third party type candidate, then even if you really like that candidate, you're actually hurting your own interest because you're making it more likely that the exact opposite of what you want actually gets voted in. So there's different solutions to solve this, maybe like a different type system. And I think a really clear example, a really good system that has a clear advantage is called ranked choice voting, ranked choice. It's also called instant runoff voting, if you ever hear that. It's synonymous. So I'll tell you what this is about. So here's a system where you go to vote, but instead of just voting for one candidate, what you do is you rank your choices. So you might say, oh, I like Mr. Ortiz number 1, and then say Ms. Hudgens number 2, and Ms. Page number 3. And then you can stop whenever you want. Like if there's a list of like 50 candidates, you don't have to rank all 50. You can just be like, here's my top 3 or 4, and then I'm done. Right? that. But then what will happen is that there be a computer system behind the scenes that tallies up all the number one votes. And if there's a majority, then great, the election's done, that person wins. But if there's not, say like that example I told you guys where, say Mr. Egan had the plurality of like 40%, but then it was 20-20, 10-10, like nobody had a majority, then what the system would do is it would toss out the least popular candidates, and then it would, because the voters had ranked their choices, now their vote defaults to their second vote. So yeah, you guys can see the advantage of that is that you can actually express your true preferences. You don't have to worry about, say, the spoiler effect or strategic voting, anything like that. Now, is the system perfect? No, you can show that it's has some limitations too, but it's a much better system than first past the post. So we're going to try this out. We're going to simulate effectively a ranked choice style vote. So I'll ask you guys who you want to vote for. I did want to do this with straw poll, but that side is down, so we'll just do a hand count. Right? Now, since we're going to be using ranked choice voting rules, what that means is that you should vote for whoever you really think on this list you want to get Teacher of the Year. And even if you're like the only vote for so-and-so, then it's okay. Just go ahead and do that, because there's no such thing as throwing your vote away. Because if somebody gets the majority, then say, okay, well, it wouldn't have mattered anyway. But if nobody gets the majority, then we'll go into like a ranked choice type process. All right, so does everybody have somebody in mind on this list? Here we go. All right, you guys are appeared for. What's up here? All right, so show of hands. Show of hands. Now you get to vote once. Okay, you get to vote once. It can be whoever you want. Don't worry about throwing your vote away. Right, so you're going to be safe with the system. Right. Who's voting for Mr. Egan? Mr. Egan. We got 1, 2, 3, 4. So I got 4 votes on Egan. Who's voting for Miss Hutkins? Miss Hutkins. We got 1, 2. Okay, so 2 votes for Miss Hutkins. For Mr. Ortiz, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, well, that's clearly the majority, but it's just for completion. Anybody vote for Miss Page? Miss Page, got 1. Okay, so Page got a vote. And how about Mr. Torres? Mr. Torres. All right, so we'll look on this vote today, but all right, so you guys see that Mr. Ortiz clearly does actually have the true majority, right? Like more than 50%. So we don't actually have to do any of the runoff thing. In fact, we could have used either of these systems and it would have come out the same. Right? But maybe here, do I have a counterexample lined up? Yeah, but let me go ahead and show you guys what would have happened had there not been a majority. So here's my last class, what they did. So got 2, 2, 7, 10, and 2. 2, 2, 7, 10, and 2. Now, in that case, nobody had more than half the votes. So I tossed out the 2, 2, and 2, and then we narrowed it down to Ortiz and Page. And then, last class, when it was narrowed down to 2, re-voted as if it had been a ranked choice type system. And Page came out, Ms. Page came out on top there. You guys voted for Mr. Ortiz. So I'm doing this with all my classes, and then I'll see if there's a winner that stands out by the end of the day. All right, so let's do some physics. Okay, so chapter 4 from your book. Also, if you guys want this written out, I did type it up for you guys. There's a tiny slip on the right side of your desk. On the right side of your desk, if you want that. Pull up. Tell you how far I got my other honors class earlier today. We did all the chapter 4 problems, and then we'll save the chapter 5 for tomorrow. So it'll probably be a similar type case with this class. Number 58. 58 says you toss a ball straight up into the air. Draw a free body diagram for the ball at 3 points in its motion. On the way up, at the very top, and on the way down. Specifically identify the forces acting on the ball. Forces.
What's the other thing?
I'll find out here. So
Okay.
you're good. Okay, I identify the forces on the ball and their agents. And then there's a couple of follow-up questions. What is the velocity of the ball at the very top? And what is the acceleration of the ball at the very top? All right, So first, some free body diagrams. Free body diagrams for throwing the ball straight into the air. Back up here, number 58. Okay. So you're down here on the ground. Okay. The ground going on. Okay. You take a ball and throw it straight up. Okay. Now, maybe I'll put a slight time axis on this, make it look a little bit parabolic, but basically it goes straight up, comes straight back down. Something like that. Okay. Well, we'll look at different points in its motion. So at some point, it's, for example, right here. At one point, it's right at the very top. And then some point later, it's coming back down. Okay, so moving up at the very top, coming back down. And let's say it's pretty much like straight up and down. That's what we care about. What did the free body diagrams look like? Well, here's what we're doing free body diagrams last week. Okay. Let's start with one at the very top. Right? What's one of the forces on the ball at the very top? About its own weight. Okay. Is there an mg? Going straight down. Okay, got that? Okay. Are there any other forces at the ball at the very top? No, that's it. Right, that's the only one. Okay. Actually, there were a couple of follow-up questions I asked about that point too. It says, what was the velocity at the very top? What is the velocity at the very top? Yeah, velocity at the top is 0 meters per second. And what's the acceleration at the very top? 10 meters per second squared downwards. Or if we said 9.8, that would be okay too. Okay, so there's parts B and C. Okay. But what about when the ball is moving upwards or moving downwards? Okay, now remember, free body diagrams, that's what we're drawing, right? FBD, free body diagrams. You only care about what kind of vectors again? Do you care about velocity vectors? No, you care about force vectors, right? Okay, so I bet this ball right here does have a weight. I bet it's the same weight as at the very top, right? Mg. And well, same story for this one too. Okay, so it's got mg, actually on, okay, all those. You know what? If you assumed a vacuum, suppose you were like on the moon or something like that. Well, the moon would be 1.6 meters per second squared, but that's like, let's say you were in a vacuum chamber. Okay? That would be the whole story, wouldn't it? That was it, and then we would be done. But you know what we started talking about last week too was air drag, like air drag. And it does say in the problem, it says you throw the ball into the air. So well, let's consider that. Now, this first snapshot, the ball is moving upward, right? Which means that air drag is pointed which way? Doesn't air drag always? Yeah, always opposes the motion, right? So yeah, say air drag is going to be going downward. F sub drag. I'm guessing it's probably going to be a smaller magnitude than the weight of the ball. That's why I drew it that way. Okay. Oh, hey, is there any air drag right at the very top? No, because remember last week I gave you guys a bonus equation, bonus formula. I said that the drag force was equal to coefficient of drag times 1/2 rho, that's the density of the air, times the cross-sectional area times the speed squared. Okay. So what I want you guys to see from that, that applies here, is that the drag force is proportional to the square of the speed. So the faster it's moving, the where's this second? Okay. All right, got that. Okay. So anyway, if you have 0 speed, there's going to be 0 drag force. Basically, right? Basically. And how about this very last free body diagram? Which way does the air drag point? Yeah, upwards. Because that would be opposing the motion in that case, wouldn't it? So I'll do F sub drag like that. Right, there you go. Okay. Now we said the speed at the very top is 0. Okay, obviously it's moving, has some speed when it's moving up and moving down. But what about acceleration? No, acceleration at the very top is 10 meters per second squared downward. Okay. What about the very first snapshot? I mean, if we're also including the air drag, you guys see that the net force on the ball is greater than its own weight? Would it make sense maybe this one's accelerating like something more than 10 meters per second squared? Maybe I'll make a side note. I'll say right here, the acceleration is greater than 10 meters per second squared. Okay. That ball is slowing down in a hurry as it's moving up. But what about when it's coming back down? You guys see how the net force is going to be less than its weight? Ooh, I bet this scenario we've got the acceleration of the ball is going to be less than perfect free fall. Would that also make sense? Because the net force is less than its weight, divided by its mass to get, I don't know, maybe like 5 meters per second squared. Number 60. Skating. Joyce and Efwa are skating. Joyce pushes Efwa, whose mass is 40 kilograms, with a force of 5 newtons. What is Efwa's resulting acceleration? 5 newton force. Well, now we do have to make an assumption to solve this one. The assumption I'm going to make is that Joyce is standing on like non-slippery ground, but Efwa is on skates. So here's J for Joyce, and here's E for Efwa. Now let's put Efwa on some skates, and Joyce, I'm gonna say, is like standing on the ground, maybe like on a ledge or something. And here's the actual ice. Okay. All right, so making some assumptions, but say the pushing force between them was, well, I'm gonna make up my own numbers that are probably pretty similar, and then you guys will have one more example to use. Okay. So I'll say the pushing force, like the applied force, let's call it, okay. Oh, 50 Newton force. Yeah, that's probably pretty good. 50 Newton force, and Efwa's mass of Efwa, let's say is just like 35 kilograms. Okay, something like that. Okay. Hey, can we just do Newton's second law of motion? I've got this force acting on this mass. So, guys, remember, you could say this: net force is equal to mass times acceleration. You usually see it written that way, but I really prefer Newton's second law of motion. I like to think of it in its fraction form. Net. Acceleration is a net force acting on some mass. So the net force we've got is 50 newtons. The mass is 35 kilograms. So what is 50 newtons acting on 35 kilograms? I'm looking at 1.4 something meters per second squared. Actually, if you look at this unit right here, Newton per kilogram, that's also a perfectly valid unit for acceleration. You could say Newton per kilogram, but you guys know meters per second squared. Of course, it's equivalent to that, so that works too. Okay, number 64. Your new motorcycle weighs so many number of newtons. What is its mass in kilograms? 64. Okay, well, let's just weight is equal to mg. Okay, mass times gravity. Okay. And they told you two of those things, so you solve for the third one. So, no, again, I'm going to change the number a little bit. Let's suppose your motorcycle weighs like 1,800 newtons. And you are on Earth, which means this number is about 10 meters per second squared. Okay. You see, you just divide both sides by 10 meters per second squared. That's how you convert from weight back to mass. You know, what planet you're on, in this case, Earth. I'm looking at 180 kilograms. Is that? So weight equals mass times gravity field. Or you could rearrange that and get gravity field as weight divided by mass. You guys remember that Paul Hewitt story with two kids on the island trying to get the Hershey bar? Okay. They're trying to figure out what is free fall gravity for these different objects. Okay. Well, and the first kid said, well, something weighs more. Here, rearrange this one. G equals weight divided by mass. This is a version of Newton's second law of motion. Okay? First kid said, well, if it weighs more, then maybe it should accelerate more, which in isolation looks good. But the other kid said, no, hold on. If it has more mass, it has more inertia, so it should accelerate less. And it turns out those two effects cancel each other out. Remember that too, right? Number 69. I got, assume a scale is in an elevator on Earth. Ooh. scale in an elevator. You guys saw a video of a guy standing on a scale in an elevator. He had the camera trained on the elevator reading, or the scale reading. You guys saw? And and you guys got some posters in this class too that talk about. So yeah, we'll solve this. What force would the scale exert on a 53 kilogram person? Well, I might change the math, but he's standing on it during the following situations. See, the elevator moves up at constant speed. The elevator slows while moving upward. The elevator speeds up while moving downward. The elevator moves downward at constant speed. The elevator slows to a stop while moving downward at a constant acceleration. Okay, so we've got this elevator doing all crazy things, and we got a person of some mass on the inside. So first thing I want to do with this elevator is solve it in terms of variables, so you guys get the big picture idea what's going on. I'll show you guys how to derive a formula where you can solve every single one of those questions. This number 69. Oh, and it split this paper in half because I'm going to do accelerating up and accelerating down.
Can I go to the bathroom, please?
Okay.
I don't know my ID though.
Okay.
Okay, thank you.
Yep. All right, so first situation I'll do is if the elevator is accelerating upward. And then we'll go back and we'll look at, well, what if it's accelerating downward? Get two slightly different equations, and then we'll put it all together. So the first situation, I've got this guy standing on a scale inside the elevator. Yeah, maybe there's like a cable pulling this elevator, something like that. Okay? I'll show you, just copy paste that picture over here for later on. Standing on a scale, elevators. Okay. Break out some sky blue ink and draw free body diagram vectors. So the sky has some mass m, got a center mass. Okay. Now, if he's accelerating upward, shouldn't there be a net force that's upward? Right? Like, I mean, I bet this guy has a weight mg. That's his weight. Okay. Same exact same story over here. This guy has the exact same weight, whatever that would be, mg. Okay. But if he's accelerating upward, I bet that the floor beneath him in that scale is pushing up more than his weight is pulling him down. Maybe it might be something like this, F sub n, where that stands for the normal force. You guys remember that from last week? The normal force? Okay. That's actually what the scale is reading. So that video you guys saw last week where the guy was watching his apparent weight change, okay, it's actually rating the force of scale pushed up against him. See how I made the normal force more than the weight? Okay. That means that there'll be net force upward and he's going to accelerate upward. Opposite story over here. If you're accelerating downward inside an elevator, isn't that like maybe partial free fall? Or maybe even in an extreme case, maybe like perfect free fall if you just cut this cable. You just like, but in a not so extreme case, maybe there's just going to be a normal force that's less than its weight. So I'll call it F sub n, and look, it's real short. It's definitely shorter than its weight. Is it? Okay. Now I wonder how the math's going to work out for each of these scenarios. Let's do Newton's second law of motion. Net force is equal to mass times acceleration. I'll start out both of them with the exact same setup. Newton's second law of motion. Net force is equal to ma. Okay. Now net force, hey, isn't that just the difference between these two forces? Now if you're accelerating upward, I would call that normal force up minus the weight down. That's what results in mass times acceleration of the guy. Right? Right, and then let's finish this out first. Suppose I want to solve for what is that normal force. What's the normal force on the sky? Is that? Yeah, that is the question also. Okay. So I'll add the weight over. So I'll get normal force is equal to mg plus ma. Okay. Oh, and couldn't he also, at that point, factor out his mass and get the normal force from reading on the scale is equal to m times open parenthesis g plus a close parenthesis, like as a group. Right? Now, how would this work out slightly differently if the elevator was accelerating downward? Well, if I want to treat acceleration as a magnitude, like as a positive value, then I would actually say the net force is weight minus this normal force, which is the opposite version of what I did before. So I'm going to call it weight minus normal force. That's equal to mass times acceleration. But then after that, I'll go ahead and solve for normal force. So normal force, do some algebra, switch some stuff around. Looks like it's going to be mg minus ma if you follow through with the algebra. Then, okay, still factor out as mass and you get normal force is equal to m times, g minus a. Interesting. So if he's accelerating upward versus if he's accelerating downward, those look pretty similar, don't they? What we could do is we could bring these two ideas together and combine it all into one like master equation. I could say that the normal force in general in an elevator is m times g plus or minus a. Now I've got a good governing equation for whichever direction that he's accelerating. You know what? You guys have actually had this formula printed out since the very first day of school. You guys remember this page right here? So there's linear motion, projectile motion. Now we're on the forces. If you look at these force equations, I'll zoom in for you guys in class. There's Newton's second law of motion. Here's friction force compared to normal force with the coefficient of friction. Here, look at this one. Tension in an elevator cable. And then here's Hooke's law down here. Now, I did solve this in terms of the normal force from the scale, but you could have also solved it for tension in the elevator cable. It would be exactly the same story. So this is also tension in an elevator cable. T it's the exact same thing. Could have solved it. Solve that perspective. So I just wrote this down here. Tension in an elevator cable. But it's the same equation. Now, before we go to the questions on the paper, let's play around with this a little bit and just see that it makes sense. So if this elevator is accelerating up, like on the left picture, then doesn't it make sense that, the normal force would have to be more than the weight? Obviously, we drew the picture that way. Yeah. So see if you plug in 0 for acceleration, like if there's no acceleration, wouldn't the normal force just be his weight, mg? And now if he's accelerating upward, it's just going to be some number bigger than that. Vice versa, over here, let's have him maybe almost accelerating downward, but what if there's 0 acceleration? This would still be consistent with that, it would just be mg. And then if he's accelerating down, that would be like partial free fall. So then you would just subtract, and there would actually be a very small force reading from the scale. At an extreme boundary condition, he might even be in perfect free fall. If you just cut this cable, is that true? You cut that cable, this goes free fall all the way down. In that case, how much is he accelerating straight down? At a rate of g. Yeah, like 9.8 meters per second squared. Wouldn't this be g minus g? That would read 0 times his mass. That would read 0 normal force. Yeah, which makes sense if he's in free fall. He would feel like an astronaut just floating around for a little short time. Or if you did perspective of the tension in the elevator cable, that would also be consistent with just cutting the cable because there would be 0 tension in a cut cable. Okay, so that makes sense so far. Now let's go to the questions. First question was, the elevator moves up at a constant speed. Let's see, show of hands. So I'll narrow it down to some options. If the elevator is moving upward at a constant speed, option A is that normal force reading is more than his weight. Option B is the normal force reading is the same as his weight. And option C is the scale reading is less than his weight. So if he's moving upward at constant speed, how many guys think that scale reading is going to be more than his weight? Nobody says that? Good. Who says it's the same as his weight? Moving upward at constant speed. Same as his weight. Guys, if you're moving upward at constant speed, what is your acceleration equal to? 0. Hey, if it's 0 acceleration, actually either of these perspectives, right? If you have 0 acceleration, isn't the normal force reading just the same as your weight? That's the answer. Yeah. So notice this. This is something that trips up a lot of students. Sometimes even teachers have seen get tripped up by this. If the elevator is moving at constant speed, it is in equilibrium as if the elevator wasn't moving at all. So what changes the scale rating is not the direction of motion of the elevator, because remember, all velocities are relative. Remember that keeps coming back in this class? It's if the elevator is accelerating. In fact, you know what? There are actually two different ways to accelerate upwards. The more obvious way is to move upwards faster and faster. But do you guys happen to remember, maybe from the spring scales lab last week, what the other way to also accelerate upward is? You can move down doing what? Slowing to a stop. Yeah, and either of those might be explained by this free body diagram. Either he's moving up faster, or this elevator is actually moving downward, but it's slowing to a stop. Vice versa for the picture on the right. He's in, looks like partial free fall. So he might be moving down faster and faster. That's the more obvious. But might actually be moving upward, but slowing to a stop. But that's what this could be. But yeah, if you're going constant speed, then the normal force from the scale is just the same as the weight. Part B, it slows at 2 meters per second squared while moving upward. Okay, now we get to break up these equations. So if you're moving upward and slowing down, then which way are you accelerating? Down, right? So isn't that like the situation on the right? Okay. So let's make up some numbers for same question, right? So normal force from the floor, or tension in the cable, if you like that way. G plus or minus A. Okay. Now, if you're moving upward and slowing to a stop, is that, so you guys are following, is that plus or minus here? Moving upward, slowing to a stop. That is accelerating down, isn't it? So it's like the minus situation. Okay. Throw a little slack in the tension cable tension, or maybe a little bit of the normal force from the scale gets alleviated a little bit. Okay. I'm going to make up some mass for this guy. Suppose this guy has a mass of like 60 kilograms. Okay. And gravity, well, let's just use Earth gravity. And suppose he's slowing down at a rate of 2 meters per second squared. Okay. Then, see, this would be the normal force reading from the scale. Okay. So that'd be 60, 10 minus 2. I'm looking at 480 newtons. 480 newtons would be the reading from that scale. Okay. That's for part B. Okay. Part A said, what if he's moving upward at constant speed? So you guys know moving upward at constant speed is just the same as being at rest. It's just like G plus, right? So just mg. Okay. So if I plug in 60 kilograms, 60 kg at 10 meters per second squared, that would have been 600 newtons. Okay. So if he's at rest at 600 newtons, if he's moving at constant speed upward at 600 newtons, if he's moving at constant speed downwards at 600 newtons. Okay. The only reason on part B that it was less than 600 newtons is because he was accelerating down, right? Moving upward but slowing to a stop. Part C, what if it's speeding up at 2 meters per second squared while moving downward? So if you're moving downward but speeding up, ooh, isn't that like a partial free fall? Actually, you know what? That is the exact same thing that we just did. If you're moving downward, speeding up, it's the exact same scenario physically as moving upward but slowing to a stop. Okay, all the numbers are exactly the same. Okay. So this is here. I'll spell this out for the video. This is moving up, slowing to a stop. Versus this scenario refers to moving down faster and faster, like picking up speed. Okay, it's physically identical in terms of forces. Part D says moves downward at constant speed. Okay. Well, we already did moving upward at constant speed. This is move up at constant speed. And we said constant speed, that means zero acceleration. That's why it boiled down to that. This is equilibrium. It would also be the scale reading if he was just at rest. Okay. Same story right here. So the normal force reading is going to be 600 newtons for moving down at constant speed. Constant speed. Okay. Because that's also zero acceleration. That's also equilibrium, moving down at constant speed. And then what's part E? Slows to a stop while moving downward. Okay, so slows to a stop while moving downward. Okay. Guys, if you're moving down and also slowing, which way are you accelerating? Well, part C, we did moving down, like speeding faster, faster. So that was accelerating down. Right? You got some of the weight was alleviated. Right? Some of the normal force was. Right? But now if you're moving down but slowing, isn't that physically identical to moving up faster, faster? It's upward acceleration. So I have to use this one. I say mg plus a. We're going to go 60 kilograms. And I made a big example, 10 meters per second squared, plus 2 meters per second squared. And see what that comes out to. I'm looking at 720 newtons. Okay, so that's the book example of moving down and slowing. But you guys know it's also identical to moving up, speeding up. Okay. Those two situations are physically identical. Okay. And then, of course, your book numbers are a little bit different, so your answers will be a little bit different. But that's should work out kind of like that. Should be pretty close. Guys, good. All right. See how we're doing here. Got 4. All right. Number 92. Number 92. Hey, this looks like an Atwood setup, doesn't it? Yeah. Let's be right here. All right. So Atwood, got a couple of weights slung over a pulley system. When we were going through that free body diagram PowerPoint last week, I got just to this point and then never quite finished with you guys. But later on this week, I'll give you guys some of these pulleys. Ooh, that spins really nice. You guys get your hands on these, some strings, some weights, and you guys get to do this lab version. I debated over the weekend whether to give you guys the lab first or do the book problems first. We'll knock out the book problems Monday, Tuesday, and then just do like a whole string of labs afterwards. I think that'd be fun that way. And so I'm sort of giving away the answer to an upcoming lab, but that'll be right. You guys get to confirm it, experiment on it. Oh, okay, I see how this works. Right, once you get your hands on the materials. So Atwood type setup. Atwood. No, this is a massless, frictionless pulley. That's one of those details that'll help make sense to the situation. There's a string slung over this. There's one weight right here, and there's another weight right there. Like 2 different lab masses, something like that. Okay. Now your textbook used 5 kilograms, 3 kilograms, so we'll make up something kind of similar. Let's go maybe 9 and 8. So let's go 9 kilograms versus 8 kilograms. Right, something like that. Okay. Now, notice in my made-up numbers that those 2 masses are really close to each other. So do you think that the system's going to accelerate very quickly or very slowly? What do you guys think?
Slowly.
Yeah, very slowly. Doesn't it make sense if they were the same, if they were like 9 and 9, that it wouldn't accelerate at all? Okay. And the other extreme condition is you could put all the weight on one side. And if you did that, what if it was like 9 versus 0? Wouldn't it accelerate down at perfect free fall? Right? This is one of those tools that's good for your mental toolkit that you can get out of a class like this before you graduate high school is play around with variables. Take things to extremes. Think, what if I make this as big as it could be or as small as it could be or the differences? Yeah, right? So one boundary condition is that they're the same mass, in which case it doesn't accelerate at all. And the other extreme is that you can put it all on one side, in which case it'd be perfect free fall. So I bet for something like this, it'd be closer to the equal situation, probably very small acceleration. But we're gonna find out. Let's do a three-body diagram. Now, there are two things that your book asks for. Your book asks for, can you find the acceleration of the system? And also, can you find the tension in the table? So now I'm going to exaggerate my picture quite a bit just to make this point. But here's the weight of this one. Oh, you know what? Since I've got numbers up here, let's just go ahead and throw in numbers. How many newtons of force, like gravity force, is that? About weight equals mg. You guys remember that? So wouldn't this be about 90 newtons of weight? Is that true? Okay. Versus this guy over here is a lot small. Well, not a lot smaller, but I'm going to exaggerate my picture a bit. Okay. Shouldn't this be 80 newtons of weight? 90 versus 80. Okay. And then now those two that I labeled are external forces. External force, external force. These are gravitational forces. It's the Earth's mass pulling on each of those. It's called a field force. Now, there is also a tension that's holding these blocks together, holding the system together. But this tension is internal to the system. Now, if you want to make this tension force sort of correct, then it's kind of like the Goldilocks force. It's bigger than the small weight, but it's smaller than the big weight. And it's also the same from on each block. See how that magnitude and that magnitude are the same magnitude, which is larger than the weight of the small one, but smaller than the weight of the big one. Is that? So it's like in the middle. But this is internal. And the reason that's important, this is an internal force, it's internal to the system, is that it's not actually part of the net force that's driving it to accelerate, driving it to move. It's not going to be part of the Newton's second law. Kind of like this. Suppose I have this pin, and I put a force on this pin, and I cause it to move, right? Cause it to accelerate. I put a force, and it accelerates. Right? Well, that force I put on it, that's like an external net force. But what about what can make like this part of the pin move versus this part? Aren't there a bunch of like molecules of plastic that are internally like binding this whole pin together? Okay. So when I move this around, what causes parts of it on the other side to move? Well, those are, that's just internal to the object itself, but it's not an actual external force. So we're going to ignore the tensions right now, and we're just going to focus on this weight versus this weight. Those are going to be the forces that are going to drive the system to accelerate. Let's plug those into Newton's second law of motion. Can I say the acceleration of the system is net force on total mass? That's Newton's second law of motion. That's the second law, Newton's second law. Okay. So the acceleration of the system is, well, it would be 90 newtons minus 80 newtons. Okay. Isn't this like a tug of war? Like one guy says, let's go clockwise. The other guy says, no, let's go counterclockwise. They're fighting each other. So you subtract, you take the difference. Okay. Again, we thought through this before. We said, well, if they were the same weight, it should be zero acceleration. And that's where it would zero out. Okay. Divided by, because I got a net force now, a total mass. Well, what's the total mass that's being moved around? Isn't it 9 plus 8 kilograms? Isn't 9 kilograms plus 8 kilograms? Remember that forces are vector values, so you could add or subtract this. In this case, you're going to subtract. But masses are scalars. And in this case, it represents, the masses represent how much total inertia is being moved around. You just add it all up. So I hope that makes sense, like why you subtract the forces on top, but you add the masses together on the bottom, right? Okay, well, we pretty much got our answer. Well, to one of the questions. What is the acceleration of the system? I've got a net force of 10 newtons acting on 17 kilograms. That's going to be 0.59 meters per second squared. That I can believe, because remember the boundary conditions. The smallest it could accelerate would have been 0, and the most it could have accelerated would have been about 10 meters per second squared. And this is definitely closer to the 0 end, which checks out because these masses are really close to each other. Like 9 versus 8 kilograms. Yeah, I can believe that. Okay, checks out. Okay. And last thing we're going to do today, solve for this tension. Now, the way you solve for tension, I'm gonna do this two ways. Is you can look at an individual free body diagram, one of those blocks. I'll do it both ways so you can see them side by side, exactly how it's gonna work out. So the block on the left is being pulled down with 80 newtons and an upward tension that we're trying to solve for. The block on the right is being pulled down with 90 newtons and an equivalent tension, but I'll show you can solve it either way. Okay. Let's go Newton's second law of motion, F equals ma. This is a net force. So the net force is the tension up minus 80 newtons down is equal to 8 kilogram block accelerating at 0.59 meters per second squared, because that was the answer that we got from before, okay, for the acceleration. Same story over here. I've got the net force is, 90 newtons down minus the tension up, solve for tension, is now equal to mass times acceleration, but this is a 9 kilogram block. Okay, so this is 9 kg, this guy's 8 kg. Okay. Also accelerating at 0.59 meters per second squared, because we just did a bunch of work to figure that out. Okay. If I do a little bit of algebra, what is 8 times, what was my answer? It was 0.588 something. Okay. Multiply that by 8, add 80 newtons. I'm getting a tension equal to 84.7 newtons from that perspective. Okay. And you really only have to do one of these, but I just want to show you it works out either way. But the other one, what is, okay, that multiply by 9, okay, and then take 90, subtract that. Okay, I'm cutting through some algebra steps because I know Bell's about rain, but if I do it this way, I get tension is, it's the exact same number, 84.7 newtons. Once you do those little algebra steps in between. Okay. So there you go. Hey, do you guys see that tension is the Goldilocks force? It's more than the weight of the small ones, but it's less than the weight of the big ones. Yeah. Hey, you guys see that? Okay, any questions? Okay, so that's a bunch of chapter 4 questions. Tomorrow we'll do some chapter 5, and then we'll do some labs after that.